The subject code is EC3552 VLSI and chip design. In that we are going to discuss about the unit 1. Unit 1 is MOS transistor principles. So what are all the topics under this unit is MOS logic families, ideal, non-ideal, IV characteristics, CMOS devices. We are going to discuss about CMOS devices, MOSFET transistor characteristics, static and dynamic conditions. So the first, in this particular video we are going to discuss about MOS logic families, in particularly about NMOS and CMOS. So in our syllabus we are given only about NMOS and CMOS. So initially we will see about the introduction. So we know CMOS, it plays an important role in the world integrated circuit industry. So and we know the basic principle behind MOS. The MOS is proposed by J. Linenfeld in 1925 and the closed structure is proposed by O. Hale in 1935. So these are all the history how this MOS transistors enters the electronic industry. So then slowly silicon planar process evolved. Even then single P or N-type transistors are favored. So we know it is good to have both polarity on the same substrate. So which was used in the low power applications. For example, watch. The processing technology which we are going to use in the fabrication of CMOS, that's the drawback. It has more complex structure. That is, the fabrication is complex than the single polarity transistors. And so NMOS production process also became complicated. So that is the threat we have in the CMOS design. So also we know the system designers, they face difficulties with very large chip sizes, power consumptions, etc. So next we will go with the MOS logic family. We know all the logic gates that are built with MOSFET devices that comes under MOS logic family. MOS logic family we can classify it into three categories. One is NMOS, PMOS, CMOS. And we know NMOS, it's built with N-channel metal oxide semiconductor, and PMOS, P-channel semiconductor, and CMOS, it is both, it combines, it is built with both N-channel and P-channel metal oxide semiconductor. So for all the MOS families, NMOS and CMOS, they are used in making an integrated circuit. It is because of its advantages. So because of these advantages, that is the N-channel MOS family, the current conduction is because of the electrons. The negatively charged electrons are fast moving than holes, which is positively charged. So the speed of operation of NMOS is faster than PMOS. And because of having both polarity, that is in CMOS, we have the less conduction. Okay, that is it, power consumption will be very less. So we are using NMOS and CMOS popularly than PMOS. And we know in the families what we are going to discuss. So we are going to discuss only about NMOS and CMOS. So in NMOS we are going to see about the universal gates. That is how to build an NMOS NAND gate, NMOS NOR gate. And the basic structure is NMOS inverter. So using this inverter only we are going to build the universal gates. So first we will see how to design an NMOS inverter. So we know here this inverter circuit, it has two N-channel MOSFET devices. So among that is Q1 and Q2. Q1 acts as a load MOSFET and Q2 acts as a switching MOSFET. Since the gate here we see is the gate is connected to the plus VVD, and so the MOSFET Q1 is always on. So the internal resistance of Q1, it acts as the load resistance RL. Compared to both MOSFETs, Q1 is designed to have more resistance than Q2. When zero voltage is given at the gate terminal, that is if you see Q2, it is turned off. It will make the output V0 to be high, which is the supply voltage. So when high input is given to the gate terminal, then Q2, that is the MOSFET Q2 will be turned on, which make the output V0 to be at the low value. That is we can see clearly in the truth table also. If we give logic 0, then the output will be high, and logic 1, the output will be low. So next we will be see about NMOS NAND gate. So here also we are using three transistors Q1, Q2 and Q3. So okay, here the Q1 acts as the load resistance, whereas Q2 and Q3 acts as a switching MOSFETs. So the two inputs here we are given two inputs A and B. So the inputs are given to both the transistors Q2 and Q3. whereas Q1 acts as the load resistance. When both inputs are low, then both the MOSFETs will be turned off, so the output will be high. Next condition, whether A or B, any of the input is low, then the corresponding MOSFET with a low input will be turned off, and so thus also making the output to be the high. But if both the terminals, both the input terminals are given high, then it will turn on both the MOSFETs Q2 and Q3, and so the output will be low. Since the supply voltage, the current due to the supply voltage VDD will flow towards the ground, so it makes the output to be the low, and we can clearly see in the truth table also. Next we will see about NMOS NOR gate. So the following circuit, here this circuit clearly shows how the NOR gate is performed. It has 3 N-channel MOSFETs in which Q1 acts as a load resistance, whereas Q2 and Q3 acts as a switching MOSFETs. If low input is given at both the inputs, then it will turn off both the MOSFETs Q2 and Q3, thus making the output to be the high, since the connection is given accordingly. If any of the input, either A or B, is given the high input, the corresponding MOSFET with high input will turn on, thus making the output to be the low. Similarly, if both the inputs are high, then it will turn on both the MOSFETs, which will make the output to be the low. This we can clearly see in the truth table also. Thus, the NMOS circuits is over. Next, we will see the CMOS logic circuit family. So, in CMOS, we know it uses both N-channel and P-channel MOSFET devices. So, this CMOS has a greater complexity than PMOS and NMOS. However, what are the drawbacks in CMOS? The speed of operation is high and the power dissipation is less. This is the most wanting advantage. So, we are popularly, CMOS grows popular because of these 2 points, because it has high speed of operation and low power dissipation. Also, it has more fan out and better noise margin. So, first we will see, similarly here also we are going to discuss about CMOS inverter, CMOS NAND and CMOS NOR. First we will see about CMOS inverter. In CMOS inverter, both the N channel and P channel devices are connected in series. So, the source terminal of the P channel device is connected to the source voltage plus VDD. The source terminal of the N channel device is connected to the ground. The gate of both the devices are connected together, and so a common input is given to both the MOSFET device. The drain terminals are also connected together as a common output. So, gate is input and drain is output. Source we are connected, okay, to the ground. N channel is connected to the ground. For a high input, for example at V in, the P channel MOSFET, that is Q1, gets turned off, but N channel Q2 will be turned on. This will drive the output V0 to be the logic low. If low input is given, then Q1 will be turned on and Q2 will be turned off. So, the output will be high. Thus, the inverter circuit is performed well. Next, we will see how a CMOS NAND gate is working. The circuit here, this circuit, it shows the 2 input CMOS NAND gate. It has 2 P-channel MOSFETs, that is Q1 and Q2, and 2 N-channel MOSFETs Q3 and Q4. Here we are taking 2 inputs A and B. Input A is given to the gate terminal of Q1 and Q3, and input B is given to the gate terminal of Q2 and Q4. And the output is we are taking from the V0. So, let us see how it is performed. For example, when both the inputs are given low input, it will turn on the devices Q1 and Q2, and the MOSFETs Q3 and Q4 will turn off. So, the output terminal is connected to the supply voltage VDD, and so the output will be held high. So, this we can clearly show in the circuit diagram, that is the truth table is also displayed below. Next case, when either of the input is high, for example, let us consider A is given high input and B is given low input. In this case, the MOSFETs Q1 and Q4 will turn on, whereas Q3 and Q2 will turn off. So, this make a path for the supply voltage to be connected to the load, thus making the output to be the high. This also clearly evidence from the below circuit diagram. And next case is if both the inputs A and B are high, which makes the MOSFETs Q3, Q4 to be turned on and Q1, Q2 to be turned off. Thus, the output is connected to the ground. Thereby, the output will be held at the low value. So this is also clearly evident from the below diagram. Next we will see lastly CMOS NOR gate. Similar to other logic family, CMOS NOR gate has also two NMOS and two PMOS, and the input and output are connected as shown in the figure. So here also for the two inputs, if A and B are held low means then two PMOS devices will conduct, making the output to be the logic high. If in next case, if any one of the input is low, it will produce a low output as shown in the figure. And the next case, if both the inputs A and B are given high input means, then it will turn on the PMOS devices, that is Q3 and Q4, thus making the output voltage to be at logic low. So this is clearly shown. Next we will see a quick recap between a CMOS and NMOS. So in CMOS it has a, first we will see about the logic levels. So in CMOS we have fully restored logic, that is the output settles at VDD or VSS, that is fully restored logic. But here in NMOS the output does not settle at VSS or ground, hence it has a degraded noise margin. So why it is good noise margin means it is fully restored logic. Next the point is transition times. The rise and the fall times are of the same order in the CMOS, but in NMOS the rise times are inherently slower than the fall times. Next, coming to the transmission gates, the transmission gates passes both the logic levels well. The output of the transmission gate can also be used to drive the input of the other transmission gates. But here in NMOS, the pass transistor transfers logic 0 well, but logic 1 is degraded. But pass transistor cannot drive the gate of the second pass transistor. Next, when we will see about the power dissipation in CMOS, almost zero static power dissipation. However, power is dissipated during the logic transition. But in the case of NMOS, with a given output, with output of a given gate is 0 means the power is dissipated in the circuit in addition to the power dissipated during the logic transition. Hence here in NMOS the power dissipation is more. Next, when coming to the pre-charging characteristics, both N-type and P-type devices are available for pre-charging a bus to VDD and VSS. Nodes can be fully charged to VDD or alternatively to VSS in a short time, but here it takes a more time. Next, coming to the power supply, voltage required to switch a gate is fixed percentage of VDD, but here it is somewhat dependent on supply voltage. Next, coming to the packing density, it requires 2 N devices for N number of inputs for complementary static gates, less for dynamic gates. But here it requires N plus 1 devices for N inputs. Next, when coming to the pull-up and pull-down ratio, load to driver device ratio is typically 1:1 or 2:1. But here the load to enhancement driver ratio is typically 4:1 to optimize the logic 0 output level and minimize the current consumption. Next, coming to the layout, CMOS encourages regular layout styles, but here in NMOS, the depletion load and different driver transistor sizes inhibit layout regularity. So all these contents I referred from the book Neil H.E. Waste, Kamran, this book, Principles. This is the book prescribed in our syllabus also. Thank you.